So yeah, I'm happy to sort of give a brief introduction, and then assuming that we have everybody, I'll just go ahead and launch into the talk, because we do have kind of a lot of material to get through.
Yeah, but tell them a bit about your prior
Yeah,
work.
yeah. So hello again, everyone. I know that we did have just a minute or two to say hello during the meetings in the afternoon, the breakout rooms on the first day. But as Kathy said, my name is Scott Davis. I'm a principal researcher at AIR. I'm a labor economist by training, so a lot of my background has been doing applied research and evaluation work focused on federal workforce programs, mostly things operated by the Department of Labor, and projects that have been implemented by Department of Labor grantees. Done work for a lot of different agencies in DOL. I've worked with state and local workforce agencies and workforce boards to implement different innovative workforce programs and evaluate those. And then Kathy and I also have a little bit of a similar background in that there was a large grant program from the Department of Labor under the Obama administration called TACT that provided community colleges with some funding to implement sort of innovative programs aimed at sort of aligning community college offerings with local labor market needs. And so I worked with a group of community colleges to evaluate their program. Kathy did as well for a different group of colleges. But I'm certainly a quantitative researcher, although I've done some mixed method stuff as part of that evaluation work as well. So hopefully that gives you a little bit about my background. And to echo Kathy, welcome to day 3, I guess. I hope you've all had sort of a wonderful experience on the first 2 days of the Institute. I'm going to be talking with you both today and tomorrow, and we're going to be talking a little bit about 2 of the more methods-oriented sessions. Today, as you can see, we're going to talk about regression discontinuity designs, and tomorrow we're going to talk about comparative interrupted time series. And each of these 2 days, I try to mention this in the breakout rooms, each of these next 2 days are going to be pretty similar in terms of the structure. So we're going to spend time this morning. I'm going to give a presentation sort of walking through the method, this method, the regression discontinuity design. Then after we're finished this morning with the presentation, we're going to distribute an activity guide to you all. You'll have time during the day to work in small groups through a handful of scenarios we've prepared to give you an opportunity to actually implement the method and sort of get your hands dirty with some actual data. So one thing I was thinking about this morning, there's quite a lot of content here in the regression discontinuity presentation and similarly for the CITS presentation. So rather than sort of pausing and taking questions during the talk this morning, I think it might be a good idea for if things come up or you have thoughts as I'm going through the presentation, things, questions that come up or what have you, it might be best to just sort of jot those down and to maybe think about bringing those up during the office hours later in the afternoon when we're going to be discussing the group work as well. It will also be able to point you to some resources that may be helpful in answering some of the questions that you might have. But I just worry that if we take too much time for a lot of discussion during the presentation, we'll sort of be a little bit too rushed. So just a note there at the outset. Okay, so I'll go ahead and get started here. So the purpose of this talk, our time here together this morning, is really to sort of introduce regression discontinuity designs and highlight some of the sort of more practical considerations that you'll face if you were thinking about applying an RDD to some CTE focused research that you may want to do. The remarks I'm going to give this morning really follow a lot of the structure and organization of some other resources that I've listed here. And I highly recommend these papers for, if you want to explore, more detail, get to know a little more of the technical details behind some of the stuff that we're going to talk about. These are really excellent resources. They also have great reference lists in each of these. So if you're looking for some of the literature behind some of the things we're going to talk about, these are good places to go. It's also worth noting that today the purpose here is really to sort of introduce the method, get you a little bit of familiarity with what RDD is about and how you use it, but we're certainly not going to go into great depth. We're not going to cover sort of everything related to regression discontinuity designs. There are a lot of sort of extensions or wrinkles or technical details that we're just not going to cover here. So I did want to just let you know that here at the beginning. Okay, so to start off, we wanted to try to motivate this a little bit by thinking about sort of the intuition behind regression discontinuity designs. And some of you may be a little bit familiar with this, maybe through your graduate work, or perhaps you've had an opportunity to use regression discontinuity. But we want to start off at a pretty basic level and just sort of set up the intuition here. So the idea behind applying a regression discontinuity design is that in some settings, programs might use cutoff scores that determine sort of eligibility to participate in a particular program. So if we're thinking about CTE, I believe you guys had the reading yesterday evening, Sean's paper on Massachusetts, studying CTE focused schools in Massachusetts. So there could be situations where there's some sort of application score that's used to determine who is eligible for a program. So there are a couple examples here. One scenario could be that schools that say have like an average test score below some threshold might be required to sort of take some steps to try to improve those scores in sort of an accountability sense. So in that scenario, the school test score is sort of in that sort of threshold is determining which schools have to meet those additional requirements. The second bullet here is sort of analogous to the scenario in Sean's paper, where if there are programs that maybe have a limited number of slots available and they have a excess demand, they might have an application process where individuals have to take a test, or they have to submit an application that gets scored somehow, and then those scores are used to determine who is offered a spot in the program. So if you're interested in learning about the effect of a program that operates this way on an outcome that you care about, as long as certain conditions hold, you can compare the outcomes for people or individuals who have scores kind of just above the cutoff, if that would sort of place them in the group that's eligible to participate. Compare their outcomes to individuals who have scores just below the cutoff. And the difference in outcomes for those two groups can tell you the effect of the program on that outcome. So the idea here, this touches on some of the things I think that were discussed in other sessions on sort of counterfactuals and the really fundamental problem of trying to identify these types of program effects. But the idea is that individuals that are on either side of this sort of threshold score and should look very similar to one another. They should be essentially the same in sort of all other respects, except for the fact that for some individuals, their score was above the threshold that allowed them to receive the treatment or participate in the program. If the other individuals who had scores below the cutoff were not eligible. So this is really sort of what you're looking for in the sort of, to be able to apply or to consider applying regression discontinuity. And that's all sort of good to know, but it can be maybe sort of difficult to think about this just sort of hearing the words. So sometimes it's easier to see this sort of in a picture. So this image is taken from one of the references that I listed there at the beginning. And really this is showing sort of the basic intuition behind regression discontinuity. So if you look at the graph, the horizontal axis is showing some measure of student poverty in this case. So as you move to the right along the horizontal axis, those data points are sort of representing students that have sort of lower socioeconomic status or sort of higher incidence of poverty according to this rating measure. The vertical axis here is measuring the outcome of interest, so the outcome that you care about. In this case, this is labeled as student score, so maybe this is a score on a standardized test or something like that. you can see there's a vertical line labeled cut point, and that represents this threshold score that I mentioned. So the idea being, if a student's poverty rating is above the cut point, or above this cutoff, then those students would be eligible to receive some treatment. So the treatment might be some additional support services or tutoring or something like that. For students that have ratings below that cutoff, they wouldn't be eligible to receive that treatment. And so the key is, if you think about the students that are represented in those boxes, those data points in the box to either side of the cutoff, the idea is that those students should be very similar to one another with respect to other characteristics that are important that would influence the outcome. And the only difference between the two is really that the box on the right, those students, their rating scores were just high enough to allow them to participate in whatever this treatment is. Okay, so if that's the case, then this jump in the outcome, this discontinuity in the outcome at that cutoff could gives you an estimate of the impact of that treatment on the outcome. Okay, so this is really just trying to visualize the intuition here behind using regression discontinuity. In regression discontinuity applications, there's some terms that you need to be familiar with. Some of these terms sort of show up with different names in different papers. The default terms I'm going to use, and really it's just for that first term, the rating variable, is the terminology that's used in that first reference that I noted earlier. So one of the terms that's important to know is what we're going to call the rating variable. So you'll also see this referred to as a forcing variable or a running variable. So this is that score variable that determines whether an individual is eligible to participate in the program or to receive the intervention that you're studying. So on the previous slide with the graph, this would be that poverty measure. That would be the rating variable, the thing that was on the x-axis. There's also a distinction in regression discontinuity applications between what are called sharp regression discontinuity designs versus what are called fuzzy regression discontinuity designs. So in a sharp regression discontinuity design, the distinguishing feature here is that it's the case that all individuals, for example, comply with their treatment assignment. So if an individual had a rating variable, had a rating score that was above the threshold, and that meant that they were eligible, say, to participate in some innovative new CTE program, then all of the individuals with scores above that threshold actually enroll in that program. Okay, so that sort of defines a sharp regression discontinuity. So the converse is what we call a fuzzy regression discontinuity design. So it can be the case, and in a lot of real world applications, a fuzzy regression discontinuity might be the more likely scenario. But it can be the case that not everyone complies with their treatment assignment based on that rating variable and that cutoff score. So continuing the sort of CTE example, it might be the case that some students that had rating scores above the cutoff, so they would be eligible to enroll in some sort of CTE focused program. Some of those students might choose not to enroll, even though they were offered a spot. Likewise, I mean, it could also be the case that there are students or individuals that had scores below the cutoff, but somehow ended up enrolling in the program, like even though technically they sort of weren't intended to be eligible. So this is a sort of non-compliance is something that, obviously this comes up in experimental studies too. So this is nothing new, but it is kind of worth noting that just using a regression discontinuity doesn't avoid problems like that, like with non-compliance. The last set of bullets here just note that there are some conditions that have to hold in order for a regression discontinuity design to be internally valid. So again, it's meaning that you're actually measuring, the treatment effect you're measuring is actually the effect of the program that you're interested in. So we've listed a few of these. So one of them is that the program itself can't influence the rating variable. So participating in the program can't have an influence on say that rating of student poverty. And this is fairly easy to sort of confirm as long as the rating variable is something that's determined before an individual would participate in the treatment that you're studying. That should be the case. The cutoff also has to be independent of the rating variable. So for example, program administrators that are enrolling students in the program of interest is sort of using this cutoff score. Those administrators can't sort of manipulate the cutoff score so that they include certain students and exclude others. So they can't sort of pick and choose the cutoff to kind of manipulate the composition of the group of individuals that are eligible for the treatment. Then the last condition here is just that there aren't any other treatments that are assigned using the same threshold. And that should be pretty clear why that would cause an internal validity problem. Because if that were the case, like if students with poverty rating above that cutoff were eligible not only to receive some support services, but maybe they were also eligible to enroll in certain classes that weren't available to others. Obviously, you're not going to be able to separate out the effects of the support services from the other courses. So you would sort of conflate those two things. So in the talk this morning, we're going to focus mostly on a sharp regression discontinuity, just to motivate the concepts and sort of explain the thinking behind the method. We will talk about fuzzy regression discontinuity and how specifically how sort of estimation is a little bit different in a fuzzy setting. But when we start walking through kind of how this works, we'll focus first on the sharp regression discontinuity setting. Okay, so at this point we wanted to pause briefly and give you guys a chance to think about some scenarios in thinking about whether regression discontinuity might make sense as an appropriate approach to estimating the impact of some program on students. So this is not the knowledge check that I forwarded yesterday evening in your email. That'll come a little bit later. But this first knowledge check, we're just going to put up these 4 scenarios. And I'll keep an eye on the clock and give everybody maybe a minute or two to just read through these. And the question here is, just think to yourself, for each of these scenarios, does this seem like a scenario where regression discontinuity would be appropriate? Okay, so I'm going to watch the clock. I'll give everybody maybe about a minute. If you want to, you can use the Zoom kind of thumbs up icon to let me know when you're finished. But otherwise, I'll just give you a minute or so, and then we'll walk through these. Okay, I'm seeing a few thumbs up, so I'll give everybody just maybe 20 more seconds. Okay, it looks like most everyone seems to be finished thinking about these. So let's I'll talk through them just quickly, give you my thinking on these. Okay, so the first scenario is a scenario where there's a high school that's introducing a work-based learning program, and they're going to admit students by lottery. So in this case, this isn't really a scenario where you'd want to use regression discontinuity, right? Like if they're using a lottery, obviously there's an opportunity here to to use experimental methods. So I wouldn't say scenario one is something where you'd want to think about applying an RDD. Scenario number two, so high school students in grade 11 take a math exam. Students that score 75 or higher are eligible to enroll in college level math courses the following year. So here, this does seem to be an excellent candidate for applying a regression discontinuity, right? So there's a cutoff score here of 75 or higher. It's on a math exam that students have to take a year in advance of the treatment. So this does look like a pretty good scenario for thinking about a regression discontinuity. Scenario three, a high school youth apprenticeship program has an application process. They score applications. They have 30 open spots, and they take 30 students with the highest scoring applications. So this scenario is a little bit trickier, I think. I would say this is maybe a maybe. So it could be the case that this is a good scenario for regression discontinuity. One of the things that I think you would want to do a little more work here to investigate this. So what you would really need to see is whether at that 30th person who was eligible for a spot in the youth apprenticeship program, were there enough other students kind of just below that 30th spot, like with application scores that were just below the score of that 30th student? Because you really need to have enough of a sample around that cutoff to be able to apply the regression discontinuity. So I would call this a maybe. I mean, this seems like could be promising, but there'd be a little bit more work you need to do to nail that down. And then scenario number four, so here there's a career readiness soft skills course. The giveaway is it's open to all interested students. So the fact that students have to give their GPAs, that sort of sounds like maybe it could be a rating variable, but in this case, there's no decision rule based on the GPA. So this isn't a scenario where you'd want to use regression discontinuity. So hopefully that was more or less in line with your thinking as well. Okay, so we've talked about some of the very basic sort of intuition behind the method. So now we're going to transition and talk through a little bit the steps you might go through if you were actually implementing a regression discontinuity analysis, sort of how just starting from the beginning. So a really good place to start a regression discontinuity analysis, like in a lot of cases when you're using other methods, is to just sort of plot your data and take a look at it and see if it looks like it meets the requirements for using a regression discontinuity. So really what you want to do is plot the data points, and all you really need here are XY pairs where the rating variable is the thing that's on the x-axis, and the outcome variable is what you're measuring on the vertical axis. So just like the earlier sort of hypothetical image I showed, that's really what you want to plot. And the key that you're looking for here is you're looking for a jump in the outcome at that cutoff score, because that's what you're using to identify the effect of this program, the effect of being eligible based on having a rating variable score higher than the cutoff. Now, I also noted here, so this is a good starting point, and it's a good exercise to go through. But at the same time, sometimes if you do this, it can be very difficult to see any sort of obvious pattern in the data. So you sort of want to start here, but you shouldn't be necessarily discouraged if you plot the data and it's there's no clear evidence of that discontinuity. But that is what you're looking for. Okay, so here's an example of what you might get if you do that. This example again is from the same resource that I listed kind of earlier. This is all simulated data. This isn't sort of data from an actual application, but you can see the rating variable is on the horizontal axis. The outcome variable is on the vertical axis. In this case, this application looks a little bit different from the way I've been describing the method to this point, because if you notice, the markers that are in blue are the ones labeled treatment, and the markers in green are the ones labeled control. So in this case, at the cutoff of 215, individuals with cutoff scores below the threshold were actually eligible to receive the treatment. So, just to note that little wrinkle. But here, I mean, if you look at this graph, I think you can make a case. It looks pretty clear that if you drew a line of best fit through each of those kind of clouds of data points on the left-hand side and on the right-hand side of that cutoff, I think you could pretty clearly argue that there's a jump there. It looks like there would be sort of a negative discontinuity at the cutoff. I mean, it's still maybe a bit unclear, but this is the sort of thing you would be looking for when you plot the data. And hopefully, if you plot the data, you get an image that looks like this that makes it very easy to interpret. But again, it's not always going to be the case. So no need to worry if you don't see something as clear as this. Okay, so graphing the data, graphing the raw data itself is really useful, but as I mentioned, it's in a lot of cases you may not necessarily see as clear of a discontinuity as was the case in that sort of simulated example. So to make it easier to judge whether there's a discontinuity at the cutoff, the next step is really to plot the data using what are called smoothed plots. And so doing this is essentially sort of a three-step process. So in the first step, you divide the data into a number of bins based on the value of the rating variable. So essentially, you can think about taking the x-axis, that axis that measures the rating variable, and on either side of the cutoff, splitting that range into a number of small bins. So each bin is going to define kind of a range of the rating variable. So in that last example, the cutoff was at 215. So if you had a bin that was a width of 5, you might have a bin that runs from 215 to 220. And so you sort of, any observations in that range would sort of fall into that bin. So you divide the range on either side of the cutoff into a number of bins. For each bin, you calculate the average value of the outcome variable in that bin. Okay, so again, just for that one example, if you identified all the observations with a score between 215 and 220, for those observations, you would calculate the average outcome score, or the average outcome among those observations. And then what you're going to plot is markers for each of the bins, where the x-coordinate for the marker is going to be the midpoint of the bin. So if the bin was from 215 to 220, it would be 217.5 would be the x-coordinate that you use. And the y value, or the y-coordinate for that pair, be equal to that average outcome value. Okay, so really this is just a way of taking kind of what could be a large number of observations in the raw data and sort of making it a little bit more manageable and a little bit easier to see patterns when you graph them, when you graph the data. There are different ways to actually choose the number of bins and how you define the bins on either side of that cutoff. So the two sort of key ways to do this are to use what are called evenly spaced bins or to use what are called quantile spaced bins. Okay, so the names sort of explain what the idea is here. So for evenly spaced bins, you essentially divide those regions to either side of the cutoff into a number of bins that are of equal size, and equal size meaning the width there when you're measuring it as a range of the rating variable. So continuing that example, if you had evenly spaced bins and they were all of width 5, then the first bin would be from 215 to 220, the second bin would be 220 to 225, and so on. So again, that method splits the range of the rating variable on either side of the cutoff into a number of evenly spaced bins that have the same width. The other option is to instead use what are called quantile spaced bins. So the difference here is when you're using quantile spaced bins, you're determining the width of the bins so that each bin has about the same number of observations in it. Okay, so when you're using evenly spaced bins, you can kind of imagine it might be the case that one bin has 100 observations in it and another bin has 10. When you use quantile spaced bins, you spread out, you manipulate the width of the bin so that each bin would have roughly the same number of observations. So then in that case, maybe you have 2 bins that each have about 50 observations in them. We're not going to get into kind of mechanics of how you sort of you choose the bins and that sort of thing. There are also ways, or I should note, so you can sort of do this yourself and just sort of pick, make ad hoc choices about sort of how many bins you want to use to look at the data. There are also ways that there are methods for identifying an optimal number of bins if you'd like to use that. And I was saying we're not going to get into the mechanics behind choosing the number of bins, but you know, just note that there are ways to sort of identify an optimal number. So as before, you know, I can imagine that it may be sort of challenging to sort of hear me say all of this and kind of think to yourself how it works. So here are a couple pictures to sort of make it easier to sort of understand this. So these are also taken from you know, the same resource that we've touched on with the other examples. So in the example on the left here, some hypothetical data have been split into a number of evenly spaced bins of length of width 10. And then the example on the right, the same data have been split into a number of bins, but here the bin length is 3. Okay, so there are a few things you can sort of take away from this. Again, remember the purpose of this is to give you an easier way to judge whether there's a discontinuity at that cutoff. That's really what you need to apply the RDD, is you need to be able to see that there's a jump in the outcome at that threshold score. So you can see that these smooth plots make it a lot easier to make that determination than just looking at the raw data. But I mean, obviously they're consistent with that raw data, but these make it easier to see. So the image on the right with the bin size of 3 makes it a little bit clearer that there's a discontinuity. So you can see that sort of adding increasing the number of bins by reducing the bin size can sort of make it easier to see the patterns here. But you can also note that you also have a smaller number of observations in each bin, right? So if you look at the size of the markers here, the size of those circles indicates how many observations are in the bin. So so you can sort of play around with the bin size and see if it helps you visualize whether there's a discontinuity in the data. And again, you want to do this sort of at the outset because you need that to be able to apply regression discontinuity. Okay, so the graphs on the last slide were just based on sort of simulated data from that regression discontinuity guide. These are some real world examples. So these are some graphs from Sean's paper that you read. In here, these are smooth plots where Sean plotted the application score, which in this case, if you look at the cutoff, it's equal to 0. So you know, you can always normalize that cutoff score to be centered around 0. And then these are plots for different outcomes, the academic achievement outcomes that Sean was interested in. So you can see, I mean, these are probably easier to interpret than the raw data, but even in this case, I mean, in some instances, it's, you know, it's not immediately clear where there's a discontinuity and where there's not. And you can sort of pair these sorts of graphical assessments with other approaches to really judge whether there's a discontinuity. But in this case, I think Sean found that there was evidence of a discontinuity in 3 of these outcomes, so A, B, and C, but not on that outcome D for passing the exit exam. Okay, so again, thinking through how you would approach a regression discontinuity analysis, you have some data, you've sort of identified that there's a discontinuity that you can take advantage of. And the next thing you want to do is estimate the effect of the intervention that you care about on the outcome of interest. So again, the goal here is to use that jump at the cutoff score to estimate the impact of the program. There are 2 approaches, 2 sort of broad approaches to doing this using regression discontinuity. So the first is called the global strategy. The second is called local strategy. And the distinction between the two is that under the global strategy, you would use all the data that you have. So thinking back to that very first image that showed some hypothetical data and it drew some boxes around groups of data near the cutoff, but there were other data points outside of those boxes. Using the global strategy, you would use all those data points, regardless of how close they were to the cutoff. Under the local strategy, on the other hand, you only use observations that are close to the cutoff score. Okay, so that's really the distinction here. We're going to talk about both approaches, but we're going to focus more on the local strategy. That's the one that tends to be more commonly used. So I'm going to next just kind of give you a sense for the global strategy and how it works, but then we'll shift gears and focus more on the local strategy. I should also point out that a lot of what we're going to talk about how you actually estimate treatment effects under regression discontinuity. A lot of these are things that are automated through statistical programs like the ones that I pointed you to in the email yesterday that you're going to use this afternoon. So this will be giving you a little bit of the theory behind some of this, but you wouldn't necessarily need to actually go through each of these individual steps on your own that we're going to talk about. So first, to touch on the global strategy, excuse me. So as I said, the global strategy uses all the data to essentially to estimate a regression model. And I also told you during the breakout rooms, we were not going to get into a lot of technical details and we would limit the number of equations. I think this maybe is the first equation. There are a handful more, but they don't get any scarier than this, I don't think. But essentially use all the data to estimate a pretty basic looking regression model. The terms in there, in that equation, the y is obviously the outcome. There's a constant in there. There's a variable t, which is an indicator for being in the treatment group. And then r is this rating variable. Okay, and there's an error term, epsilon. So f of ri is some unknown function of the rating variable. So we don't sort of know that relationship a priori. That parameter beta 0 is really what we care about and what we're trying to estimate, because that's telling you the effect of the program at the cutoff of on the outcome of interest. So since we don't know the true form for that function, f, applying the global strategy sort of involves testing out some different alternatives for that function, and then sort of identifying the one that seems to fit the data the best. So in practice, you can sort of test out different functional forms for that function f. So if you include just a term in the regression for the rating variable itself, just r, so that would be a linear function of r. You can add a squared term to make it a quadratic. You can add r cubed, make it a cubic. You can do some other things to make it flexible. So you can interact some of those terms with with a treatment indicator, for example. But essentially, what you do is sort of think about a few different models and estimate those, and then you can look at tests like at F tests to choose the model that looks like it's the best fit. Once you've figured out which of the models fits the data the best, then you can go and do some sensitivity tests. One way of doing this is to go back and re-estimate your preferred model, but to sort of drop some of the observations at either extreme of the rating variable. So you can go back and re-estimate the model and drop, say, the outermost 1% of the rating variable values, or the outermost 5% or so on. So you're sort of excluding observations on either tail of the rating variable. So you would sort of do that and see if your point estimate is very sensitive to those exclusions. And if it is, that's sort of a suggestion that maybe that functional form may be misspecified. So that perhaps the estimate is really being driven by some of those extreme observations. Okay, so that's the global strategy, and that's all we're going to talk about with respect to the global strategy. Again, the difference between the global strategy and the local strategy is whereas the global strategy uses all observations to estimate the treatment effect, local strategy uses only those observations within a selected boundary around the cutoff. So you can think about looking at your data, and you're going to use only some data points that are within a window around that cutoff score. The range around the cutoff score that determines which observations you're going to use is called the bandwidth. So as an example, if the cutoff score was equal to 50 and you had a bandwidth of 10, then you would use all observations that had rating scores between 40 and 60 when you go to estimate your impact. The way that you can estimate the impact of the treatment in a regression discontinuity setting using the local strategy follows, there's sort of a series of steps here. The basic intuition is you essentially estimate two separate regression models, one using the data on either side of the cutoff. So you estimate a regression model using data to the left of that cutoff score, and you estimate a separate regression model using data, only the data points with rating scores to the right of the cutoff. And you can use a similar type of regression model as we showed for the global strategy, where the outcome is just a function of a constant and in the rating variable and an error term. Sort of like the global strategy, that function f is unknown. You can try different ways of modeling that unknown function. If you just use the term r there, that would be what's called a local linear regression, because you're modeling the outcome as a linear function of the rating variable. You can add higher order terms again, so you can add in addition to having r in the regression, you could also include a squared term, an r squared term. If you add those higher order terms, then that approach would be called a local polynomial regression. Okay, so but in any event, you're sort of doing the same thing no matter what model you choose. You're estimating a regression on either side of the cutoff. Once you've estimated those two regression models, the next step is you take the estimated coefficients from those regression models and you generate two predicted values. So you generate a predicted value of the outcome at the cutoff score using each set of the estimated regression coefficients. So if you imagine having a set of regression coefficients that you got when you used the data to the left of the cutoff, you take those estimated coefficients and you generate a predicted value of the outcome at the cutoff score. You do the same thing using the estimated regression coefficients that you got when you estimated the regression using the data to the right of the cutoff. And that's going to give you two predicted values for the outcome at the cutoff score. Then the last step is to just take the predicted value that you got when you estimated the regression, or when you estimated it using the coefficients above the cutoff. You take that, and from that you subtract the other predicted value, the one you got when you use the coefficients from below the cutoff. And you may be noticing a theme here, because this is another instance where I can imagine that it may be a challenge to sort of follow a lot of the sort of verbal description here, but I think a lot of times it's much more effective to sort of see an image and sort of be able to think through how this works. So this is a picture that that really shows the intuition behind the local strategy. So this graph is showing what's going on when you're implementing a local strategy. So you can see here, again, the horizontal axis is measuring this rating variable. There's a vertical line at the cutoff score that's labeled C. There are also vertical dashed lines showing the bandwidth on either side of that cutoff. So the bandwidth is defined by H in this case. So the data points that are within the bandwidth are the ones that you use to estimate these local regression models. The data points in red on the right of the cutoff represent data points for the group that would be in the treatment group. The data points in blue represent observations for the comparison group. So again, what you do is take those data points on either side of the cutoff and estimate a regression model using each set. So if you look at the black lines in the picture, and hopefully those are clearly, hopefully this is big enough where you can sort of see those. The black lines show those regression, those lines of best fit from a local linear regression. So this is if we estimated a regression model where we just have an R term on the right-hand side. So you would get those black lines. So you can see that the predicted values I was talking about are given by where that black line crosses that vertical line at the cutoff. So you can see there's an intercept based on the red data points that's labeled, it looks like U hat or mu hat with a plus. There's also an intercept from the line of best fit through the blue data points, that's labeled mu hat minus. So to get the estimated impact here, you would just subtract U minus from U plus. That jump, again, it's that jump in the outcome is telling you the estimated impact of the treatment. For what it's worth, in this picture, the solid blue and solid red lines show the lines of best fit from local polynomial regression. So these are, if you added some higher order terms to those regression models instead of just using a linear model. Okay, and I should also mention this image is from another one of the resources that I noted at the beginning, and this resource is really comprehensive. If you want to know a lot more of the sort of technical details behind regression discontinuity. So one of the key things that you have to do when applying the local strategy is you have to pick a bandwidth. Right, so you have to decide sort of how large is that window around the cutoff that you want to use to estimate the impact of the intervention. So it's worth sort of noting, there's a trade-off here when you're choosing the size of that window. So for any given kind of functional form, again, that functional form relating the rating variable to the outcome, choosing a smaller bandwidth is always going to make the model do a better job of approximating that true unknown function. So essentially by reducing the bandwidth, you're always going to reduce the potential bias from your estimate of that functional form. So that's good. Like reducing bias is good. But at the same time, if you use a smaller bandwidth, you're also reducing the number of observations that you have available to estimate that regression model. So the trade-off there is that's going to reduce the precision of those coefficient estimates. So reduced precision is not good, right? So there's a trade-off here when you're trying to determine the bandwidth that you want to use. Because of this trade-off, rather than approaching it as just sort of making your own subjective judgment about what bandwidth makes sense, there are kind of sort of empirical methods that have been developed for choosing a bandwidth, and we're not going to go into detail about those, other than to say the statistical commands that you would use to estimate a regression discontinuity model would have those types of bandwidth, optimal bandwidth selectors baked in. So just know that there is a way to sort of choose the best bandwidth. Okay, so suppose you've chosen, you've got the data, you've confirmed there's a discontinuity, you have maybe estimated a treatment effect, and you're sort of thinking you may have some good evidence of the effectiveness of some program like a new CTE program. As part of your analysis, you really also have to assess some of the critical assumptions underlying the validity of the design. So really some of the key assumptions deal with that rating variable and how it's determined. And essentially what you really need to be convinced of is that it hasn't been manipulated in a way that that the groups of individuals on either side of that cutoff have been sort of manipulated to include or exclude certain types of individuals. Again, the regression discontinuity is only valid if those two groups, the group immediately to the left of the cutoff, the group immediately to the right, if those two groups are essentially the same, except for the fact that that one group was eligible for the treatment. So if individuals were somehow able to manipulate their rating score, so if they knew what the threshold was and they knew they were slightly below the threshold, but somehow could manipulate the score so that they end up slightly above the threshold, then that sort of destroys that that baseline equivalence of the two groups. Okay, so there's some ways that you would go about sort of testing or sort of trying to confirm that that isn't a problem in your analysis. So we've listed some common approaches here. So one good starting point is just to learn how the rating variable was created and how the cutoff score was determined. So this can be pretty simple. So you can talk to the people the program administrators who assigned the ratings, whoever determined the cutoff. You can review program documentation that explains how kind of the rating process or the assignment process. You can kind of compare the actual ratings to how they were supposed to be determined, that sort of thing. Really, it's just sort of getting as much information as you can on how the rating variable was assigned to just confirm that there aren't any problems. Second approach is to analyze the probability of participating in the program, the probability of receiving the treatment. So to do this, you can essentially plot the same type of smooth plots that we talked about earlier. And in order for the design to be valid, there has to be a jump in the probability of participating in the program at that cutoff. So if you look at a plot of the probability of participating in the program and you don't see any sort of jump at the cutoff, that means that your design is not really able to identify that treatment effect. Another validation test that you can do is to use sort of a similar graphical approach with those smooth plots, but to look at variables that are not outcomes. And so these would be variables for which you would expect the treatment to have there'd be no reason to expect that the treatment would have an effect on those variables. There are a couple different types of variables that are commonly used for that type of test. So one would be any type of variable that's determined before the treatment assignment. So for example, like if there are sort of participant demographic characteristics, like if you have like a baseline test score or something like that, you can look at a graph and see if there's a discontinuity at the cutoff in that baseline test score, because there shouldn't be. Another type of variable would be that you could use here would be what are called placebo outcomes. And so these are outcomes that would be determined, say, after the treatment assignment, but you wouldn't expect them to be affected by the treatment. So if there's some other outcome variable that really, should have no relation to the program that you're studying, looking for discontinuity at the cutoff for that outcome can sort of help you judge whether the design's valid, because you should see no discontinuity. If you do, that sort of suggests something else is going on there that would call into question the internal validity of the design. And then the last type of test listed on this slide is to look at the density of the rating variable. So again, what you're looking for here is whether there's any evidence that individuals were able to manipulate those scores so that they could sort of just get past that threshold. So if you're thinking about the scenario where that's not the case and you have a good design, if you focus on a window, really a small window around that cutoff, essentially you would expect sort of the number of observations with scores just below and just above the cutoff should be roughly the same. It's almost as if at the cutoff score, or in that small window around the cutoff score, individuals were essentially assigned at random. That's sort of what you would expect to see. So if you look at the density of the rating variable around that cutoff, and you see that the number of observations with scores just below the cutoff is abnormally low, and the number of observations with scores just above the cutoff is abnormally high, that would be a concern, because then you would sort of need to investigate further, but it would provide some evidence that people might have been able to manipulate that rating variable. Okay, there are some other types of sensitivity tests you can do as well. I'll try to go kind of quickly through these. So one is you can look at what are called placebo cutoffs. So you can look at the rating variable and sort of test or sort of look graphically for a discontinuity at some other value of the cutoff other than sort of the official threshold score. If you see some other discontinuity, that's a problem. You can use something called the donut hole approach to test for manipulation of the rating variable. So this approach really relies on kind of the intuition that if you're thinking about the individuals that would be most likely to be affected by manipulation, it would be those individuals that are really close to the cutoff. So if you estimate your model, but you drop the observations really close to the cutoff in some really small window around the cutoff, and that's what the donut hole refers to, is you're sort of dropping those observations right in the middle, and then you re-estimate the treatment effect. You can sort of do that for a few different windows around the cutoff, and if you see your point estimate changing quite a bit, it sort of suggests that that maybe there may be potential manipulation. And the last type of test here is using different bandwidths. So recall the bandwidth is defining that window around the cutoff that sort of determines which observations you're using. There's this trade-off between bias and precision when you're choosing a bandwidth, but you can, once you've estimated treatment effect, you can sort of go back and try a little bit smaller, a little bit larger bandwidths and see what that, see if your point estimate is sensitive to that choice. So if you're sort of getting the same results regardless of varying the bandwidth, that sort of suggests that that it's not the choice of bandwidth that's driving the result. So that would be good. Okay, and there are more details about all of these sensitivity tests and how to implement them. Again, it's some of the resources that we've mentioned. Okay, so now we're at the point where I had sent everybody in an email, and I hope you all have it, a handout that showed some checks that we were going to do to just kind of give you a chance to think about how these sort of validation tests would work. So if you have a moment now to pull that up and sort of take a look at it, there are, I think, just four different sort of scenarios. So like we did before, I'll give everybody a couple minutes to kind of read through these. And each of the scenarios is just giving you sort of the outcome of a different type of validation test. And the idea here is for you to think about whether, just based on what we've talked about, whether each of these scenarios would give you sort of cause for concern or sort of call into question the design. So let me look at the clock. So I'll give everybody about a minute, and we can do the same thing. Once you're finished, you can maybe give me a thumbs up on Zoom, and then we'll go through each one together. Okay, I've seen a few thumbs up. Looks like people might need a little bit more time to maybe look through these, but I'm sort of keeping an eye on the clock and knowing that we still got a little bit more material to cover. I think I'll go ahead and sort of run through the thinking behind these, and then later, if you want to go back and sort of think about these a little bit more when we're finished, you can certainly do that. So the first scenario is you're speaking with someone about a CTE program that was using an application process to select students, but the program sort of advertised that if you had a good recent attendance record, that would help you get in the program. And so the idea is this could potentially pose a problem because students can control their recent attendance. They the outreach materials would have made students potentially aware of that, so students could have tried to manipulate their application scores. So I think there's some potential here for this to be an issue. I think you would need to do a little bit more digging to really know for sure whether this is a concern, because just because there's these sorts of conditions doesn't mean that individuals were able to manipulate their rating score in a way that would be problematic. So for that first scenario, I think you would need to do a little bit more analysis before you'd be able to judge whether it's a problem. The second scenario, so you have a graph here of the probability of receiving the treatment. The cutoff is 68. There's a clear discontinuity at 68. The probability of receiving treatment jumps quite a bit from just below to just above that cutoff. So no reason to be worried about the design because of that. Number three, here you've plotted a placebo outcome, and you would be concerned if there was some sort of discontinuity at that cutoff of 50. But looking at the plots, there's no evidence of any sort of jump. So again, here I don't think there'd be any sort of concern about the validity of the design based on that result. And then for the last scenario, number four, so this is just a histogram of the number of observations with different scores for the rating variable. There's a dashed line at the cutoff. If you look at that on either side of that cutoff, the number of observations that are just below the cutoff is quite low. It's the fewest number of observations in any one of those bins. The number of observations with scores just above the cutoff is abnormally high. So in this case, I think yes, this would call into question whether the design's valid, because here you would be concerned that there was some sort of manipulation of the rating variable. Okay, and I may speed up just a little bit so that I can make sure that we finish on time here. So to this point, we've been focused, as I said, on sharp regression discontinuity. We've been assuming that the cutoff completely determines whether an individual actually receives the treatment. But as we noted before, there can be non-compliance with treatment assignments. So there can be no-shows, in other words, people that were eligible to participate that end up not participating. And there can also be people that were not eligible to participate that somehow did. We call those crossovers. So again, this is something that's common in experimental settings as well. In regression discontinuity, if it's the case that the treatment assignment, that there was non-compliance with the treatment assignment, and it can be in a variety of ways, we would say that you would apply a fuzzy regression discontinuity design. Here's another couple of pictures to sort of show you what this looks like. The sharp regression discontinuity examples on the left, the fuzzies on the right. The vertical axis is measuring the probability of receiving the treatment conditional on your rating score. So you can see in the sharp example, everyone who had scores above the cutoff actually received the treatment. But in a fuzzy regression discontinuity setting, some individuals that were eligible to receive the treatment and assigned to the treatment group actually didn't receive it. Okay, so one way you can sort of figure out if you're in a sharp or a fuzzy setting is, again, look at those individuals who were eligible for the treatment and see if all of them actually received it. Estimating the treatment effect in a fuzzy regression discontinuity context is a little bit different than in the sharp setting. The reason for that is that remember, we're thinking about those two groups representing those boxes on either side of the cutoff. In a fuzzy regression discontinuity setting, those groups can include sort of a mix of participants and non-participants. So it's not necessarily the case that they are essentially equivalent in all the ways that matter. So there are a couple different approaches you could take when you're in a fuzzy regression discontinuity setting. So one would be to just ignore non-compliance and just estimate the treatment effect using the sharp regression discontinuity approach. And you can do that, and that'll generate an estimate called the intent to treat effect. And that's telling you that estimate is telling you the effect of the program on those individuals who are eligible for it, regardless of whether they actually participated. And sometimes you may be interested in that point estimate. A more common approach is to estimate what's called a local average treatment effect. and that represents the marginal effect of the treatment on those who comply with their treatment assignment. So it's the effect of the treatment on the treated, essentially, or the effect on compliers. So to estimate the local average treatment effect, it turns out that that effect is equivalent to the jump in the outcome at the cutoff divided by the jump in the probability of participating, or the probability of receiving the treatment at the cutoff. So you can actually calculate the local average treatment effect using this ratio. So the numerator there is just the sharp regression discontinuity estimate of the jump in the outcome at the cut point. And the denominator is the jump in the probability of receiving the treatment at the cut point. So you can kind of just calculate this ratio to get the local average treatment effect. But in practice, essentially to estimate this in a fuzzy setting, most people would use an instrumental variables approach and estimate a two-stage model. So the two regression equations here, the first shows the treatment indicator. So this is an indicator of whether an individual actually participated in the treatment as a function of a variable D, which is an indicator for whether they were assigned to the treatment. Again, some function of the rating variable, a constant and an error term. The second stage models the outcome as a function of the treatment and the rating variable. So essentially the way this would work is you would estimate this using two-stage least squares. You would estimate the first regression equation and then use those coefficients to generate predicted values of t. Then you would plug those predicted values of t into the second equation in place of the actual variable t and estimate that second model. And you, sort of like the global strategy, you could test out different functional forms here of that function, those functions f1 and f2. And again, in practice, a lot of this will be sort of automated by the types of statistical programs that you would use. There are a few other topics in regression discontinuity that we're not going to cover, but we did want to just sort of touch on. One is to note, or a few notes about precision. So generally speaking, if you're thinking about applying a regression discontinuity design, you're going to need a much larger sample than you would, say, if you were able to design and carry out an experiment. So on the order of like double to 4 times the sample size. And the reason for that is because the designs have sort of reduced precision compared to like an experiment. So you need to sort of compensate for that. And that's called a design effect, just if you ever come across that term. The other note about the precision is if you want to use non-parametric methods, you need a larger sample size than if you use parametric methods, and you also need a larger sample for a fuzzy regression discontinuity than for a sharp. There are lots of ways. So we've sort of touched on the basics. Again, the point here was to give you a little bit of an introduction to the intuition and some of the mechanics behind applying regression discontinuity, but there are lots of ways you can make these types of models more complex. So we've listed a handful here. So one extension would be to allow for multiple cutoffs. So assignment to the treatment group could depend not just on a single cutoff, but it could be contingent on the rating variable falling in a particular range. So both below a lower bound and or above a lower bound and below an upper bound. So that you can sort of modify the model to account for that. There could also be multiple scores. So assignment of the treatment can depend not just on a single rating variable, but on multiple rating variables. So for example, it might be the case that students applying to a new CTE program have to have minimum math and reading scores, minimum scores on both a math test and a reading test or something like that. Just like you can have clustered experiments, you can have clustered regression discontinuity designs. The idea here being that it could be that schools are assigned to some sort of treatment depending on a school level aggregate score, but you have data on student level outcomes, and that's what you want to, that's what you're interested in. So that would be sort of like a clustered design. You can combine regression discontinuity with experiments. So that here you start getting more complicated. So for example, if the rating variable is some sort of measure of student need, It could be the case that maybe there are two cutoffs, and students below the lowest cutoff are assigned to the comparison group, so they have low needs, so they're assigned, they aren't eligible for the treatment. Students above some higher threshold are assigned to the treatment because they have a high need. But then in between those two cutoffs, maybe students are assigned at random, either to be eligible for the treatment or not. So you can sort of design, there can be complex designs that sort of mix the two. And then there's been recent work too about adding what's called a non-equivalent group. We'll just touch on that. The idea is essentially to add to the basic regression discontinuity setup a separate untreated comparison group. So the idea there is if you think that the functional relationship between the rating variable and the outcome is parallel for that untreated group to the main comparison group, then that non-equivalent, that untreated comparison group gives you a little bit more information. And so some of the things you could do are sort of improves your precision. It allows you to do some extrapolation farther away from the cut point. Okay, so essentially that's the end of what we're going to talk about as far as sort of the theory and maybe some of the mechanics behind regression discontinuity. We did want to note that there are what works clearinghouse standards that apply to regression discontinuity designs. And essentially really what those standards deal with are the sorts of things that we talked about that you need to confirm for the validity of your design. So the integrity of the rating variable, that you don't have attrition problems, that the continuity assumptions are met, that the bandwidth and functional form is appropriate, and then there are standards related to fuzzy RDDs specifically. So RDDs can be rated meet standards without reservations if they satisfy all those individual standards, or they can be rated meet standards with reservations if they satisfy some of them. So, and I would encourage you to look, you can look at the What Works Clearinghouse Standards Handbook for specifics about RDDs and sort of those standards. Okay, so we spent a long time sort of this morning just walking through the intuition behind the method, how you use it to estimate treatment effects, and some of the ways you would want to sort of confirm the validity of the design and that sort of thing. And all of that was sort of, we called that sort of the theory section of today's session. So now what we're going to do is shift a little bit to what we're calling the practice component. So for this practice component, really the idea here is to not just give you an introduction to the ideas, but also let you work with real data and practice applying some of these techniques. So there's sort of two pieces to this. So first, I'm going to talk for another 20 minutes and demonstrate some examples. I'm going to show you, focusing on Stata, some hypothetical scenarios as sort of what output looks like when you're doing some of the things we talked about. And then the rest of the afternoon, or the rest of the day and through the afternoon, you're going to be able to work in your groups through a series of activities that we've designed. Everything I'm going to do through the rest of our time this morning is going to focus on Stata, but all of the commands that I'll show you have equivalents in R for people that use R. As you know, you'll also have time to meet with our trainers in virtual office hours later this afternoon, where you can ask questions. Again, you can ask questions about anything that came up this morning that we didn't have time, that I asked you to sort of hold, or you can ask questions about the group activities. So I'm going to walk through just to sort of motivate what I'm going to show you. We came up with a hypothetical scenario. So this is very similar to the sort of setup of Sean's paper, where you can suppose that a state has a number of CTE focused high schools. Students have to apply for admission, and they have to their application has to meet some threshold to be eligible to enroll. We're going to assume, for what I'm going to show you, that all the students that are accepted actually enroll in the schools. So we're going to use RDD to estimate the impact of attending the school on an outcome. The data in the example I'm going to show you is all hypothetical. It's derived from a political science application, but we sort of manipulated it a little bit just to make the numbers look a little more reasonable. There's some key variables. Y is the outcome. You can imagine that this is like a grade 12 test score. X is the rating variable. This is an application score. It has a cutoff of 50. and Z1 is just a generic sort of student characteristic. So you can maybe think about this as like a baseline test score or something else. So since we assumed every student that applies, or every student that is eligible to enroll actually enrolls, this is going to be a sharp regression discontinuity setting. Okay, so we're going to walk through sort of the steps that we described. So step one was we want to plot the raw data. So here we've done that using Stata's two-way command to just produce a scatter plot. The rating variable X is on the horizontal axis, the outcome Y is on the vertical axis. There's a line, a vertical line at the cutoff of 50. So I mentioned earlier, sometimes it can be hard to make much sense of the data. So if you look at this, I mean, I wouldn't believe anybody that told me they could see a discontinuity here. So this is an instance where, you know, looking at the raw data is a good first step, but it doesn't really tell you too much. So this sort of also emphasizes the advantage of using the bins. So the next step was to plot the data using some bins. So here, I've just chosen arbitrarily to use 20 bins, so 10 on either side of the cutoff. And I'm using Stata's RD plot command. So the commands that I noted in the email yesterday, one of them, RD density, automatically also installs this RD plot command, I believe. So, so this is something you can use to generate these types of smooth plots really easily. So in the Stata syntax, you have to tell Stata where the cutoff is. So that's what the C option is, with 50 as the argument. It's telling Stata that the cutoff is at 50. And then number of bins, 10 on either side. That bin select option here, that's actually the default for Stata. If you specify a number of bins, then that bin select option doesn't apply. But if, for example, we didn't want to pick the number of bins, we wanted to let Stata choose the optimal number of bins, then we could just delete that in bins option. And then Stata would use the equal spacing, mimicking variance bins, which are optimal. So here you can see again, the point is we've made the data much easier to look at. And now it's clear that there is a discontinuity at the cutoff. The dots are those average outcomes for each bin. And you can see this command automatically produces a polynomial fit to the data. In this case, I think it's a fourth order polynomial is the default. But again, the point is here, it's much easier for you to see that there's a discontinuity. Okay, this next slide reproduces the last one, except now we've doubled the number of bins, just again to show that how when you manipulate the number of bins, what that does to sort of what you can see in the plot. And I think here, really the key is those polynomial fit lines haven't changed because they're based on the raw data, not the binned data. And those really are what make it easy to see the discontinuity. You can see more bins sort of, you know, adds the number of data points that you're looking at here. Okay, as the last example, we've just doubled the number of bins once more, so now there are 80. You know, again, the polynomial fit lines don't change, so you're still seeing the discontinuity. One thing to note is that when you start having more and more bins, sometimes you can get a bin that's really dominated by an observation that has sort of an abnormally large or small value for the outcome. So if you notice, the scale of the vertical axis has changed here a little bit to accommodate that data point that's all the way up near 80 or just over 80. So that can happen if you start using a really large number of bins. But again, those polynomial fit lines don't change. Okay, here all we've done is put those 3 previous graphs on the same slides. You can sort of see what happens when you're sort of increasing the number of bins. So personally, I mean, I think either the 20 bins or 40 bins looks good and it would sort of be helpful to think about the data. I would maybe lean towards the 20 bins myself, just because it sort of looks, I think it looks cleaner. But the point, again, is to use these types of graphs to judge whether there's a discontinuity at the cutoff, because you need that in order to apply the RDD. Okay, if you've confirmed that there is a discontinuity again at the cutoff, so that you're good to go on applying RDD, the next step that you would think about doing would be, again, trying to confirm that there's no evidence that the rating score has been manipulated. So in this hypothetical scenario we're thinking about, this would mean that students that were near the cutoff but below it weren't somehow able to bump up their score, so they just get over that threshold to be able to be eligible to enroll in the CTE high school. So here we're just plotting a histogram showing the number of observations with different values of the rating score. So the rating score is on the horizontal axis. The cutoff is still 50. In the state of commands here on the left, the first few lines basically execute this RD density command, and it does that quietly just to not produce the output. Because when you run that command, Stata stores the optimal bandwidths as results. And so that's what those, so then the next two lines just take those optimal bandwidths and store those as a local macro that we can use when creating the histogram. So all that code at the bottom is just generating this histogram, and it's coloring the bars for observations below the cutoff blue and observations above the cutoff red. So remember, this is sort of like the example in the handout. It's the same sort of scenario. What you're looking for here is, on either side of the cutoff, does it look like there, to the left, the number of observations is really low, and to the right, the number of observations is really high? So in this case, there's no, there isn't really any evidence of that. There is that sort of really narrow bar just at the cutoff, but that's sort of an artifact of the display that I couldn't quite figure out how to correct. But really, the thing to look at are those two bars on either side of that little gap, and you can see that there's no real obvious evidence of manipulation. Okay, so now on this slide, we're using another test for manipulation by looking at the output of this RD density command. The key here is that what this is doing is plotting the estimated density around the cutoff. In this case, because those lines represent the estimated density, the gray shaded areas are confidence intervals around those. In this case, because the confidence intervals overlap, there's no reason to think that the rating variable was manipulated. Additionally, some of the output here sort of includes a formal test statistic that I didn't show, but that also confirms that. A third way you can look for manipulation is to actually just use a binomial test. So if you think about a small window around the cutoff, again, the idea is that if there's no manipulation, then it should be more or less, it should look more or less like observations were assigned to the treatment or not, just by chance. So if you look at that first line there, just looks at the number of observations close to that cutoff of 50, and calculates the proportion of those that were in the treatment group, and that turns out to be 53%. And then the second line just executes a binomial test to see if that percentage is meaningfully different from 50%. And if you look at those test results down there at the bottom of the output, you can see that the test statistic is not statistically significant. So in that case, you can't reject the null hypothesis that there's no manipulation. Okay, I see we have about 5 or so minutes. We may run over just a minute or two if that's okay. To estimate the treatment effect, again, remember that what you can do is estimate separate regressions and then subtract two predicted values that are based on those regression coefficients. So this is just to show you that actually works. So the code here estimates those two regressions and it takes that difference. The thing to keep in mind is just look at the bottom where the RD estimator is 2.151. Okay, so just remember that. You wouldn't actually do this in practice, but it's just to sort of demonstrate this. So if you estimate the treatment effect using the RD robust command, using a first degree polynomial, so a linear model, a bandwidth of 10 and a cutoff when the cutoff is 50. The panel on the right shows you the output from RD robust. And if you look at the bottom, that coefficient listed is 2.1511. So if you compare that to the panel on the left, which just reproduces what was on the previous slide, you see that you do indeed get the same thing. So you get 2.1511, whether you actually go through those intermediate steps of estimating two separate regressions, or you just rely on Stata's on the RDD Robust package to estimate the model for you. Okay, so here we just chose an ad hoc bandwidth of 10. This next example estimates the model using the same RDD Robust command. All the arguments are the same, except here we've changed the type of model we're using from a linear model to a quadratic. So you see that P argument is the order of the polynomial. So the 2 there means that we're including an R squared term in that model. So now the coefficient has changed a little bit. It went from 2.151 to 2.16. And in this case, it's not statistically significant. And you can see that with the p-values there. The RDD Robust command, you can also change the way you choose the bandwidth. So in the previous examples, we were just picking a bandwidth of 10. Now you can see we've used this bandwidth select option to pick the mean squared error optimal bandwidth. If you look at the bottom, the coefficient in this case is gotten a little bit larger. It's 2.16. You can also see the p-values associated with it. So this is the last example here of actually estimating the treatment effect. Here we've done the same thing, except in this case, we're allowing for there to be different size bandwidths on either side of the cutoff. So the MSD2 bandwidth selection method allows you to sort of select separately the optimal bandwidth on the left and the optimal bandwidth on the right, and they don't necessarily have to be the same. You can see now the estimate changed again to 2.24. And I'll also mention all of these, how these Stata commands work are sort of detailed pretty well in the Stata help, or the help files available on the website I pointed you to, as well as in the paper, one of the papers that I noted on the early slide. We already sort of looked at an example of this in the handout, but you can do a falsification test by just plotting the data, but replacing the outcome variable y with one of these other variables like z1. This is what you get when you do that. I think this is actually the same output as we used in the handout, but it just goes to show you there's no evidence of a discontinuity here. In addition to looking at the plot, you can also just estimate the treatment effect using RDD Robust for your your falsification test. We're using a different outcome variable here that shouldn't be affected. And if you do that, if you look down at the bottom, again, the coefficient's nearly 0. It's not statistically significant, so there's no reason here to think that the design would not be valid. Okay, I sort of ran through some of that at the end relatively quickly to try to keep us on schedule. But like I said, if you have any questions, we can certainly discuss those during office hours. And I would encourage you also, we can send you those references. I think you might also be able to look through some of those and answer some questions you might have, because again, all of these slides were largely based on those materials. But just quickly to let you know what's coming next. So after we conclude here, we'll send you an activity guide that we prepared. The guide has a sequence of 4 scenarios with a bunch of questions associated with them. You'll work through those as a group using the data sets that we sent yesterday. You have the rest of the day and afternoon to work on that. Each group is going to meet, have some time with the trainers to meet for office hours to talk about your progress, ask questions, whatever, however you want to use that time, is up to you. The agenda should already let you know who you're meeting with and whom, and you should have a link and a meeting invitation. And then at 4:30, we'll reconvene as a group just to recap a lot of what we talked about today and see how things went, and just sort of conclude the day. Okay, these are the references that that we had touched on, and these were noted earlier. And then I will end as well, putting up the disclaimer slide just so I can say that we did indeed put up the disclaimer. Okay, so we're a couple minutes over, but let me pause there, and I appreciate your attention and patience. I know it's an hour and a half of listening is can sometimes be a challenge, but hopefully that gives you a little bit of an introduction into some of the basics of applying RDD.